is Chashi, who is going to tell us how to remove the party-dependent overhead in perfectly secure MPC online dependence.
Thanks for the introduction. Good afternoon, everyone. My name is Xiaxi. It's my pleasure here to introduce our work to you. This is a joint work with Yifan Song. We construct a perfectly secure MPC protocol which achieves constant online communication. In the setting of MPC, there are n parties participating in the computation, and t of them are corrupted by an adversary. We will focus on the optimal resilience, which means n equals to 3t plus 1. We assume for each pair of two parties, there is an authenticated and synchronous channel. The goal, on the one hand, is to ensure all honest parties receive correct outputs, which will be referred as GOD with no error probability. On the other hand, we ensure the adversary can only learn the output and nothing else. Our focus is to optimize the communication complexity. And in this table, we will use C to denote the circuit size, D for the circuit depth, and for the number of parties, and the communication is counted by the number of field elements. Focusing on the setting of malicious security with GOD, there are two remarkable results: the work by Bioliava, Trubiniava, and Hart, and the work by Goyo, Liu, and Song. Focusing on their overall and online communication, they both have a term C times N. However, if we move to the semi-honest security, there are also two remarkable results. The work by Damgaard and Nielsen achieves overall communication of all C times N elements, and the recent work by Escudero and others optimizes the online communication to OC elements, which is irrelevant of the number of parties and without blowing up the overall communication. This online communication can be interpreted as constant elements per gate. Therefore, going back to our setting, we ask, is it possible to construct a perfectly secure MPC protocol which achieves constant online communication without blowing up the overall communication? Why do we care about constant online communication? There are two reasons. Firstly, the preprocessing phase, which only depends on the circuit size, can be done in the IDLE time. Secondly, this implies that when the number of parties increases, the average communication per party will decrease. Our construction gives a positive answer to the previous question. In particular, we achieve online communication of OC elements and preserve the overall communication to still be OC times N elements. But our result has two limitations. The first one is that our construction only works for finite fields of size larger than 2n. This is due to the use of Pierre-Meyer secret sharing and hyper-invertible matrix. The second one is that since we are using the dispute control framework, our run complexity will grow with the number of parties. As a relative mention, there is a line of works focusing on optimizing communication without ON overhead in the run complexity. The recent work by Abraham and others achieves overall communication of OC times N and OD run complexity. Recall, D is the circuit depth. And if expected constant round Byzantine agreement and broadcast channels protocols are used to instantiate our construction, our run complexity will become OD plus N squared. Both our work and the work by Goyo, Liu, and Song have run complexities growing with the number of parties. Focusing on the overall communication, the second work removes the quadratic communication overhead in the circuit depth. Both our work and the first work have this term. Hence, as a future direction, we ask, can we achieve the best among these three works? The rest of my presentation will have three parts. Starting from semi-honest protocol computing SIMD circuits, we gradually compile it to achieve full security and towards computing general circuits. Before that, let's start with the concept of Pierre-Meyer secret sharing, which stores case secrets using a higher degree to preserve the secrecy. It is linearly homomorphic and multiplicative friendly. For the later one, we mean that All parties can obtain their shares of the multiplication result by locally multiplying their two shares. Here, star means the component-wise multiplication. In our construction, we set k equals to t plus 2 over 2, considering both the communication benefits and security. MPC functionality is often represented by arithmetic circuits over finite fields. In generic approach, all parties compute their shares for each y value. This can be extended to SIMD circuit, which consists several identical copies of a single circuit. If we choose k equals to omega n, then all parties can compute omega n copies at the cost of just computing one copy. Let's start with the semi-honest protocol for multiplication gate, adapted from the work by Escudero and others. In the preprocessing phase, all parties prepare a packed beaver triple with their shares of x and y. They locally compute their shares of x plus a and y plus b, and then send to a common party, p king, who reconstruct the secrets and distributes 2 degree k-2 packed Shamir sharings of x plus a and y plus b to all parties. All parties locally compute their shares of z by consuming one packed beaver triple. After that, all parties use a pair of double sharing to do the degree reduction. They first compute their shares of z plus r, send them to p king, who reconstruct the secrets, and distributes 1 degree k-1 packed Shamir sharing of z plus r. Then, in the end, all parties locally compute their shares of z. Considering the communication, this has already achieved constant elements per gate. However, if we move to malicious setting, in the first and third step, the adversary can send incorrect shares to p king. In the second and fourth step, the adversary may distribute packed Shamir sharings that are not of degree k-1 or with incorrect secrets. To achieve full security, we rely on the dispute control framework, which is proposed in the work by Bieliava, Trubiniava, and Hart. In this framework, all parties initiate an empty set to keep recording the set of dispute pairs. After uniformly dividing the circuit into n-squared segments, they compute all the segments sequentially. For each segment, they first evaluate and then verify the computation. If the verification passes, all parties move to the next segment. If it fails, then they are supposed to identify a dispute pair. And then they reevaluate the current segment. They repeat this procedure until all the segments are successfully computed. Importantly, corrupted parties will be eliminated, and two disputed parties will communicate with the help from a relay party. This method is proposed in the work by Bensasan, Fehr, and Ostrovsky. In doing this, two disputed parties will never talk to each other. This is critical for us to ensure the communication does not explode due to the reevaluation. Based on this framework, we need to realize efficient verification and identifying dispute pairs when faults occur. When corrupted parties send incorrect shares to p king, since the whole sharing is determined by the shares of honest parties, by choosing k properly, then p king can detect the errors by locally checking whether the received shares form packed Shamir sharings that are of degree k-1, the degree t plus k-1, or of degree t plus 2k-2. Also, all parties need to check whether p king behaves honestly. This can be abstracted as all parties check whether they hold correct pairs of sharings of U. Notice that these pairs of sharings are determined by shares of honest parties. To do this, starting with n-t pairs to be checked, they expand them to n pairs by locally multiplying them with a Vandermonde matrix, and then reconstruct each pair to a distinct party who checked the correctness of the received pair. Notice that there are n-t pairs checked by honest parties. If all honest parties are happy, then by superinvertible property of Vandermonde matrix, all n-t pairs are correct. Until now, we have achieved batch-wise verification with O(n) elements per pair. When verification fails, either p king complains the received shares are incorrect, or one party, say pi, complains the received pairs are incorrect. In the second case, PI can ask Peking to provide a correct version, and then to identify a dispute pair. And in the first case, since packed mirror sharings are of high degree, then Peking cannot identify which shares are incorrect. Our idea is to use the degree T Shamir sharings and take advantage of their error-correcting property. And importantly, we do not want to explode the communication. To this end, all parties silently compute degree T Shamir sharings for each Y value. Notice that they can locally transform K degree T Shamir sharings to packed sharings. When verification fails, by relying on the error-correcting property of degree T Shamir sharings, a dispute pair can be located. However, using the current protocol to compute cross-layer multiplication can still suffer from the so-called double-dipping attack introduced in the work by Goyo, Liu, and Song, and we propose a simpler method to resolve this issue. For more details, please refer to our paper. Now we move from SIMD circuits to general circuits. To compute general circuits, we are supposed to prepare input sharing for the next layer. It requires us to collect secrets from different packed sharings and align the secrets to the correct order, which is referred as network routing in the work by Goyo, Policraniado, and Song. Based on the previous works, this can be reduced to prepare random linear masks. To prepare random linear masks for different linear transformations, notice in the target correlation, the ith secrets are stored at the ith position. Our observation is that if all secrets are stored at the same position, then they can do the linear transformation locally, thanks to the linearly homomorphic property. Based on this observation, we aim to prepare K random linear masks. We emphasize that these K linear transformations can be possibly different. In particular, all parties first perform a transpose operation on the secrets to ensure all K secrets of each pack sharing are stored at the same position. Then, based on our previous observation, they can apply the linear transformation locally. At this time, K secrets of each pack sharing are still stored at the same position. Again, they apply another transpose operation on the secrets. Eventually, they obtain the pack sharings with secrets after linear transformations. As a result, we have reduced preparing random linear masks for different linear transformations to performing transpose operation, which is a special kind of linear transformation. And to perform transpose operation, this can be reduced to preparing random linear masks of the same kind. This can be done in the preprocessing phase. As for the communication, the online communication remains to be ON elements per linear transformation as required. To summarize, starting from the semi-honest protocol to compute cross-layer multiplication, we propose a simpler method to resolve double-dipping issue. And to compute general circuits, we use the idea of transpose to efficiently handle sharing transformation, which makes it as possible for us to reduce different linear transformations to a specific one. Aiming at achieving constant online communication, we make use of the packed mirror sharing, which adds difficulty for us to realize efficient verification and identifying dispute pairs when verification fails. Putting things all together, we eventually get the perfectly secure MPC protocol, which with online communication of O1 elements per gate and ON elements per gate. That's all my presentation. Thanks for your listening.
We have time for questions while Giovanni sets up. If there are no questions, we can all read the paper, and thank you for your talk.